Okay, so in class what we saw is the sequential key search problem, which is a classical search algorithm. So if you're given an array of integers in any arbitrary order, they need not be sorted, just some arbitrary randomly generated array, and you want to search for a specific key, then you go through a loop from index 0 to n minus 1, and for each index you compare the value at that index a of I with the search key k. If you are equal, then you have found the key at that particular index. Otherwise, you keep going to the next index until you reach the last index. And if you manage to find the key by then, you should have stopped the search and said you have found the key. If you are not able to find the key by going through the entire array, you come out of the loop and say you have not found the key. So that's the simple logic for a classical key search, and I've given you the code for doing the same thing. Let us see the C++ version of it. So you're generating here, let me make it a little bit more bigger. Okay, so you're generating the code here, the getting the inputs for the number of elements and the max value, and then setting up the random number generator and generating the array. I'm using a pointer to point to the array, and then so here I have from 0 to 1 less than the max value. Okay. In your assignment, you'll be doing 1 to max value. So if you want to do that, you add a 1 to what are the random number generated. So you'll have from 1 to max value. Accordingly, you can change this from this to this. Okay. So I'm going to, the logic is this. For a particular search key, this is what the code we saw. You will run from index 0 to n minus 1, which is in this case num elements is n. So n minus 1 will be, so that's why index less than n num elements. And then I'm going to keep track of the number of comparisons you do as part of the search process. So for each index, you'll compare the value at that index with the search key. So that's one comparison. So we're incrementing the number of comparisons, which is initialized to 0 before the beginning of the for loop. And now here I want to do the search for several keys. So I don't want to stop the program right after finding the search key. I want to continue to the next search key. So I set a boolean called search success is true and then break from this for loop. And the purpose of search success is this. So you run now an outer for loop for different search keys from 1 to max value, and for the particular search key you search for that key in the array, and if a search was successful, you don't need to go through after the for loop because you're really done with that search key. If the search was not successful, that means the search success was initialized to false and it was not turned back to true within this for loop. That means you have not found the search key throughout the execution of the for loop. So so that means you come out of the for loop without breaking out of it, because you break out of the for loop according to this logic only if you found the search key. Otherwise, you go through all the iterations in the for loop and come out of the loop, and that's when you will hit this block of code where you test if the search was successful. Such success will be still false and not of such success will be true, and you can add the number of comparisons to the total comparisons. So total comparisons would be set before the before the search loop, and the num keys is also initialized to 0, and for every key you increment num keys, and depending on the number of comparisons you do either for a successful search or unsuccessful search, you keep incrementing the total number of comparisons. Now, what we are going to do in this assignment is called sequential block search. So the classical search will take big O of n time, and you want to do it more optimally by taking less time. So we want to do it in less than n, so square root of n is less than n. But one requirement for doing sequential block search is the array has to be sorted. So we are assuming that the array is sorted kind of for free, and we are not going to count the sorting time in this assignment. The idea for sequential block search is this. So let us say you have a sorted array of integers like this, and you want to say search for 450. If it was a classical search, you will compare 450, the search key, with every element in the array until you hit the element 450. Whereas in the sequential block search, what we're going to do is we're going to fix a block size. So in this case, is the array of 10 elements, and let us say the block size m is 3. Okay, so that means you're going to compare the search key first with elements at indexes that are increments of the block size. So basically the idea is to find the particular block where that 450 could be there. So that means you're going to compare that with elements at index 0, m, 2m, 3m, and so on. So that's what I have indicated in the description here. So you're going to compare the search with elements at 0, m, 2m, 3m, and so on, as well as with the last index. Okay. So you're going to compare with 0, then 3, then 6, then 9. Now the purpose of doing such comparisons is you want to find, since the array is sorted, you want to find with which block the search key could be there, within which block. So 450 is greater than the element here as well as greater than the element here, so it's not going to be within this block. Similarly, it's greater than this one and greater than this one, so it's not going to be within this block, and so on. So it's greater than 445, and this is the last index, which is the last index we'll compare that with, and it's less than 489, less than or equal to 489. So you will, once you identify the block, then you go through a sequential search process, okay, from the beginning of that block to the end of that block, and you will be able to find the element there. Now let us do for one more example here. So you first compare 356 with this element at index 0, it's greater than this one, and then so you check if it's greater than or equal to this. So you can have, say, two index variables, the beginning of the block and the end of the block. So if the block size is 3, the beginning of the block is going to be index 0, the end of the block is going to be 2, and the beginning of the next block is index 3. So you could compare with elements at index 0, and then the elements at index 3, and then 6. Now you see, for 356 it is greater than or equal to 56, but it's also greater than or equal to 178. So it cannot be like that. It has to be greater than or equal to the left index, and then this index, and then less than or equal to the next index. So if that's the case, you have identified the block. Like so, now in this case, if this is greater than or equal to 178 and less than or equal to 372, so that means 356, if at all it's located, it's going to be in this block starting from 3 and ending at index 1 less than 6, because this is not the last block, because this is not n minus 1. So the block will range from 3 to 1 less than this index. Only for the last block, it will go from that 9 to that index n minus 1 itself. Okay, and then once I identify the block, you're going to do a simple sequential search within the blocks, starting from the beginning index of that block all the way to the last index of the end index of that block, which will be 1 less than the next block index. Okay, so for the blocks like 0, m, 2m, and so on, you will go from that m to 1 less than the beginning of the next block index. So that's why if you see the description, so the block that you find out, or that the search key could be there, it's called as the targeted search block. And if the targeted search block is not the last block, then you will search from that beginning index of that block, which is p times m, which is like 0, m, 2m, 3m, and so on. So p is that integer, 2m, 3m, 4m, like that, to p times m plus m minus 1. So this would be the last index within that block where you can search for. If the targeted search block is the last block, then let us say it starts from p times m index, it goes all the way to the last index n minus 1 if it's the last block. Okay, and if you don't find the element within that block, it's not going to be anywhere else because of the nature. For example, if it's 200 is your search key, it's going to be greater than 0, the element at index 0, 56, and less than the element at index the next block index m. So that's it's not greater than, sorry, it is greater than 178. So it is not going to be within this block. So let us move to the next block. Is greater than or equal to 178, less than or equal to 372. So this is the right block. If at all 200 is there, it should be here. Then you do a sequential search starting from the beginning index of this block, which is 3, and you have 178, then 247, 356. So that's the last index of this block you can search for. The next index 6 is actually the beginning of the next block. So you search through all the elements in that block, which is the targeted search block, and 200 is not there. Then you can conclude 200 is not here. So at the worst case, you have to do like the number of blocks you'll have is n over m. So you will have to kind of compare with 0, m elements at index 0, m, 2m, 3m, and so on up to n minus 1. So that will be n over m blocks. And once you have identified the targeted block, within a targeted block, at the worst case, you have to do m minus 1 comparisons, because actually m comparisons. You have to do m comparisons because there will be m elements within a block. So you have to do m comparisons within a block. So totally you will have n over m plus m. So at the worst case, you have to do that many comparisons. You have to go through elements at index 0, m, 2m, 3m, all the way up to n minus 1. That will be n over m comparisons. Plus within the particular targeted search block, you have to do m comparisons. So that will be n over m plus m comparisons. So that's a theoretical result, which is very straightforward from this and little differentiation. So you want to find out what is the so you see here n is a array size, is a fixed quantity. So only parameter that can be varied here is this m, the block size. So for what value of m you will encounter the minimum number of comparisons at the worst case. So that's what we are interested at now. So we can say the number of comparisons is a function of m for a given n. So we'll differentiate that number of comparisons with respect to m, and differentiation of n over m, n is again a constant, so it will be minus n over m square. Differentiation of m with respect to m is 1. So you can equate this differentiation, the differential to 0. So c prime of m equals 0. That will be like for the optimization. You want to find what for what value of m this function will have a minimum value. So minus n over m square plus 1 equals 0. That means n over m square is 1. So that is m is equal to square root of n. So if the block size is square root of n, then the number of comparisons you do will be minimum, not only the worst case but also the average case, because once you prove it for worst case, that's also the same thing for average case. So you want to verify this, that the average number of comparisons is minimum when m is square root of n, now using simulations. And that's what you're going to do in your code. You're going to try for a given n, you're going to try for 3 different values of m, which are like n to the power 1 over 3, n to the power 1 over 2, and n to the power 2 over 3. So let me go over a sample code. So this is the code actually you will be working on, sequential block search student code. The earlier code I went through is just to show you a sample code for sequential search. So The sample code on classical sequential search is a complete code. You can run it without adding anything to that code. But the file that is named student code is the version that is like a startup code that you have to build on top of it. So this code has already the function to sort an array. So I have used a selection sort algorithm as a sorting algorithm to sort. So in the main function you input the number of elements, the maximum value, and this is where you find the block size, which is n over that 1 over 3 or 2 over 3 or 1 over 2. So you can use the pow function and to find and then raise the exponent there, and you kind of typecast to an integer because the block size has to be an integer. And then you generate the array using a random number generator process, and then run the search loop as we saw. And then once you generate the array, you also get the array sorted. So I have all the code already written for you. I have the sort function using which you can sort the array. And then so you're going to work on the sorted array after that. So initialize the total comparisons to 0, num keys to 0, and start the for loop for the search key. So search key runs from 1 to max value, and for each of the search key you're going to search for that key in that sorted array. So initialize num comparisons to 0 for that particular search key. And this is like if your since the array is sorted, if a search key is less than the element at index 0, that means it's not going to be there at all. So it's like, for example, in this case here, if your search key says some 30 or something, it's less than the first element 56, so 30 is not going to be in this array at all. Similarly, if the search key is like 500, which is not here, it's not going to be which is greater than this 489, the last element. Since the array is sorted, you can just compare the search key with the element at index 0 and the element at the last index, and if it is less than the element at index 0 or greater than the element at the last index n minus 1, then you can right away say the element is not there and go on to the next search key, and that's what I'm doing here. So increment, because of we are doing two comparisons here, so set up the number of comparisons, increment it by 2, and then you're done with that particular search key in this case. So you add that, so only when you're done with that particular search process, either successfully or not successfully, then only you add num comparisons to the total number of comparisons. And then when this continue statement will take the control to the next search key in this for loop, because it's continuous within that for loop, and all the languages have such a feature. And so when your control comes beyond or after this if statement, that means the search key is within the range of the elements in the array. If at least the magnitude, if it could be there in the array or need not be there, but at least the magnitude. So for example, like what I mentioned here, if you're searching for anything like the 3 values mentioned here, they're not going to stop at this stage prematurely because it's not less than 56 or not greater than 489. So you're going, the magnitude of the elements you're searching for is within the range of the elements in the array. So you're going to do a sequential block search like what I was explaining. So that's the implementation you have to do. So that means within that code that you will develop, you have to find the number of comparisons you would need to that takes into consideration moving with first comparing with the block indexes, and once you identify the targeted search block, you have to search only sequentially within that targeted search block, a simple sequential search, and take care of the number of comparisons that you encounter, again for both successful as well as unsuccessful search depending on the search key, and add it to the total number of comparisons. And so when you're done with that all the search keys, you can come out of that for loop and print the total number of comparisons, the average number of comparisons, by dividing the total comparisons with the number of keys. Okay. So the Java language has this loop labeling feature. So because you need a nested loop because you already have a search loop for the search key, and then remember this the sequential block search algorithm. What you have to do is you have to first go with the block indexes, and then once you identify the particular block, you have to run a sequential search within the block. So you definitely need a nested loop. and depending on whether once you identify the particular targeted search block, you don't have to go through the rest of the blocks in that sorted array. So you have to break from a certain loop and then go to another loop. So to transfer control, it becomes easier if you can label the loop, but only Java has that labeling feature of loop. So you can use label the loop and move to control to the outer loop depending on which loop you want to transfer the control. In C++ and Python, you don't have that feature of labeling the loop, but you can use a boolean like I've used here in the sample code, the search success like that. But you see here, I break from this loop and I want the control to immediately go to the next search key. But here I have a nested loop again here, so I cannot label this loop and say continue to the search loop here, whereas in Java I can do that. So what I do to get around the situation is I use a boolean called search success. I initialize it to false, and when I find the search key, I set it to true and break. There's a break statement allowed and continue statement allowed, but you cannot use break from this loop or break continue from to this loop and so on. So when you use the break statement in C++, almost in all the languages, what happens is in a nested loop, you break from the innermost loop wherever you are. So the control comes out of the innermost loop and you stay here. But you don't want to execute the rest of the statements here if your search was successful. So that's why you make use of that boolean and it's check if the search was successful. If the search was not successful, then only you want to add the total number of comparisons, the number of comparisons to total number of comparisons. If the search was successful, you would do that here itself, and you don't want to really execute this block of code. So you kind of mimic the continue, because if the search was successful, you're not going to execute this block of code, and control then goes to the next search key in the outer loop and then runs the rest of the code for that search key. Okay, so this is how you can handle in C++ as well as in Python by using a boolean variable, one for each loop, and depending on whether you want to break or continue, you have to adjust the logic accordingly. Okay, I'm giving kind of hint how to kind of handle nested loop in C++ and Python. So then what you do is, so you see here, so for a given n, the number of elements, you can find the block size by using this pov function. So you can set it to 1 over 3 or 1 over 2 or 2 over 3. So for a given n, you have 3 different m values. Okay, so your n values, you're going to try for n equals 100, then 1000, 10,000, and 100,000. And then now the max value for any element in the array for all the simulations, you're going to have 50,000. So that's fixed. The max val that you're going to input is going to be always 50,000. So for each value of n, you can vary m. So for a given simulation, of course, for a given n, you try to find the m within the code and run the simulation and compute the average number of comparisons for that n and m. Tabulate it and then go back, and for the same n, change this to the other m exponent, 1 over 3, and then to 2 over 3. So you will tabulate the n versus m values. So you totally have 9 combinations, not 9, you have 4 n values. So you have for each n value 3 m values. So 4 times 3, there will be 12 cells in the table. Okay, so 4 n values, and for each n value you'll have 3 m values, so totally 12 different values you will find as part of the average number of comparisons. And then you can plot in Excel the like something I'll quickly show you the kind of charts I'm expecting. So the n values and the average number of comparisons you get. So this is something like what I got. So you will plot them, and you can right click on the Excel chart, add trend line, and go to options. Of course, type, you can choose the power function and go to options, and you can click display equation chart and display R square value. Of course, this is Excel 2003. For each Excel version, this could be a little different. So you'll get a power function and you'll get an R square value. So depending on which R function you are different, you can do, depending on which R m. So each is for a m. So this is, say, for m equals 1 over 3, m equals 2 over 3, and this is for m equals n over 1 over 3, m equals n over 2 over 3, or n to the power of, and this is m equals n to the power of half. Okay, so m equals n to the power of half is expected to give you the smallest value for the number of comparisons, and m equals n raised to 1 over 3 and m equals n raised to 2 over 3 are expected to give you a larger value. And so I would expect you to get similar curves, and you can use the trend line option to get the power function. So this is like, okay, the number of comparisons is y, and x is the array size, and raised to an exponent. So the exponent is expected to be between 0 to 1. Okay, so you have to do all the simulations and get the values like what I am showing here. Similar to that, you cannot get exactly the same numbers. If you copy from this Excel file and show the numbers, I can easily find it out. So you have to run your code and get all these numbers, and I can verify with your code. Okay, so I'll also run your code and see if I'm getting those numbers. So you can do it in C++, Java, or Python. I have given you the startup code. Again, since I gave you the startup code, you have to extend only that code and finish your assignment. You cannot use any code of your own. Okay, and you have to submit all these things. So actually, you can put together all these things in a PDF file, and this is the code file. So you would only have two files that you submit: the code file and items 2, 3, 4, 5 put together as a PDF file. Okay, so the version I'm going to upload in Canvas will tell that in detail. Okay, so that will stop this video.